Welcome back to the deep dive. Today we are swapping the office chair for a scaffold plank.
Sounds good to me.
We're diving into the world of concrete masonry units, the CMU. And not just the basics. We are getting granular with the gray matter itself.
That's right. If you're building anything in Canada, sooner or later, you run into that stamp on the block.
That cryptic code.
Yeah, something like H15AM.
Hmm.
And, most people see four symbols. We see four fundamental properties that dictate everything about that wall.
Exactly. Our mission today is to crack that code. This is our code cracker guide to the Canadian CSA A165.1 standard.
We need to translate it.
Yeah. From that abstract spec sheet language into practical knowledge you can actually use on site, whether you're laying block or, let's be honest, just trying to organize a delivery.
And understanding these specs is, well, it's paramount. They govern everything from structural load to fire safety to just its durability against our climate.
Get the code wrong and the whole thing fails compliance.
The whole wall. It's a big deal.
And it is a system with multiple dimensions, a bit like a diamond, actually.
A diamond. Okay, go on.
Why is the CSA A165 system like a diamond?
I'm waiting.
Because it has four facets, and if you don't understand them, you are definitely going to be under a lot of pressure.
Ah, okay. A fitting analogy, especially when you think about compressive forces. So let's start at the beginning. Let's decode that H15AM example facet by facet.
Perfect. Facet 1, the first letter, this tells us about the guts of the block, right? The solid content.
Exactly. It's all about how much air versus how much concrete is actually in the unit. The standard workhorse is H.
For hollow.
For hollow. That's your typical block with the large cores, the voids. But if you're designing for, say, a specific structural need or a really high fire rating, you'll see alternatives.
Like an S.
Right. You might see S for semi-solid or even SF for full solid. We're talking units with 75% or even 100% solid content.
And that solid content is a huge predictor of how it's going to perform.
Thermally and structurally, yes.
Which leads us right to facet 2, the number. In our example, it's 15. This is all about strength.
Correct. The number 15 stands for 15 megapascals. MPa. It's the minimum compressive strength, and it's calculated based on the net area of the block.
So 15 MPa is the standard, but it can't be the only option. I imagine a foundation for a house is a bit different from a high-rise shear wall.
Exactly. 15 is just the starting line for serious load-bearing stuff. For those really heavily loaded application spaces of tall buildings, critical shear walls manufacturers offer blocks at 20, 25.
Or even higher.
Or even 30 MPL.
Yeah.
And it doesn't change the block size, but it fundamentally changes the mix design and the quality control at the plant.
I saw an apprentice crying over a pallet of 30 MPL blocks the other day.
Oh, yeah.
I asked him what was wrong, and he said, nothing. They're just really heavy hitters.
That's a good one. When you're stacking those, you know you're dealing with serious material.
Okay, moving on to the third facet. This one is, I'd argue, the most relevant to the person actually laying the block.
The one that affects your back.
Exactly. Facet 3, concrete type or density, represented by the letter A.
A stands for normal weight. These units have an oven dry density over 2,000 kilograms per cubic meter.
So heavy.
Very heavy. They're made with traditional dense stuff like limestone or silicious gravel.
And then you have the installer's best friend.
The lightweight options, yes. The CSA system defines progressively lighter blocks with letters like C or D.
And what's the weight on those?
Well, Type C is around 1,700 to 1,800 kilometer, and Type D is the lightest, coming in under 1,700. They use aggregates like expanded shale, expanded slag.
Things that reduce the mass.
Significantly. And that reduction in mass is a massive factor when you're, humping blocks all day.
Oh, 100%. Why did the mason cancel his gym membership?
Let me guess.
Because he spent all day doing block presses with 12-inch hollows? Who needs a barbell when you have a 40-pound CMU?
The labor savings are huge. It's a core reason we see so many lightweight blocks now.
Okay, final facet. Facet 4, the M in our example, moisture content.
M for moisture controlled. This is a crucial technical detail for the wall's longevity.
What does that mean, controlled?
It means the units are intentionally dried, pre-shrunk at the factory. The goal is to minimize shrinkage once they're in the wall, which reduces the chance of random cracking.
And if you see an O?
O means non-moisture controlled. That block could shrink a lot more after it's laid. For a designer, seeing an O is a huge red flag.
A red flag to do what?
To meticulously plan for control joints. You have to design for that movement, accommodate that dimensional change.
Let's stick with those lightweight blocks for a minute, the Type C and D. They're easier to lift, sure, but their composition must change how they interact with water.
It does. Because they use those porous, expanded aggregates, they have inherently more internal void space.
And that's a trade-off.
It's the crucial technical trade-off. That porous aggregate affects the maximum permitted 24-hour absorption limit in the standard.
So a normal weight block might have one limit.
Right, a Type A block might be limited to, say, 175 kilobarameter, but a very lightweight Type D unit can be permitted up to 300 kilobarameter.
Wait, hold on. That higher absorption rate sounds worrying. If a wall is absorbing that much more water in a test, isn't that a massive risk on a job site?
It's a logical question.
Does it mean the lightweight wall is less resistant to rain once it's built?
That is a very common line of thought, but it's a critical misconception we have to clarify. The source material is clear. The absorption limit does not imply less resistance to in-service water penetration.
So what is it for then?
Its main function is as a surrogate indicator. It's an indicator for the unit's resistance to freeze-thaw deterioration.
Ah, okay, so we're not checking for waterproofing. We're checking for long-term durability in a cold Canadian climate.
Precisely. The wall assembly as a whole, the mortar, the flashing, the finish, that's what determines water resistance. The block's absorption limit just gives us confidence it won't fall apart when it gets saturated and freezes over and over.
That makes so much more sense. That decision, Type A versus Type D, it's a major design calculation, not just a casual swap.
And the place where that density decision matters most is fire resistance.
Absolutely. When we talk fire resistance rating, or FRR, it's tied directly to two of those facets.
Facet 1, solid content, and Facet 3, the density. The rating is determined by the unit's equivalent thickness, how much actual material is there, and the concrete type.
Okay, let's use an example. A standard 190 mil hollow block, an 8-inch unit, maybe 56% solid. If that's made with Type A normal weight concrete, what's our FRR?
You're looking at around 1.8 hours, which is solid performance.
But this is where it gets really interesting. You take that exact same 190 mil hollow block, but you make it with a lightweight Type C concrete.
Or what the National Building Code might call an L220S density standard.
Right. What happens to the rating?
It jumps to 2.5 hours.
Wow.
You gain almost 40% more fire resistance just by changing the aggregate type. Same size, same solid content.
So the lightweight aggregate is a better insulator.
It provides superior thermal performance. It slows the heat transfer much more effectively than the denser, normal weight material.
That's critical info for a designer. Now, what about grouting? You said the FRR is based on equivalent thickness. If I partially grout that wall, does that boost my rating?
You'd think so, but no. Not for calculation purposes.
Really?
When a wall is partially grouted, say for some vertical rebar, the fire rating is conservatively assigned the same FRR as a fully hollow wall.
So the grout doesn't count?
The contribution of the grout is ignored. The hollow section is seen as the weakest link, so it dictates the overall rating.
Continuity is everything. Okay, speaking of performance, what about sound? Noise reduction is often the inverse problem of fire resistance, isn't it?
It is. We've established that for fire resistance, lighter can be better. For sound performance, the opposite is generally true.
More mass, less sound.
Exactly. The sound transmission class, or STC, ratings are directly linked to mass. A 10-centimeter hollow block, for instance, is typically STC 40 to 43. The heavier the concrete type, the better the acoustic isolation.
And all of this performance feeds into the bigger picture of fire safety strategy. CMU construction is, by its nature, non-combustible.
Which makes it a fundamental part of passive fire protection and what's called a balanced design strategy.
Yeah.
Concrete doesn't add fuel to a fire. It maintains its structural integrity under intense heat, and it compartmentalizes the fire. Unlike an active system, like sprinklers, which can fail.
Passive protection is just there. It's built in.
Always there, structurally sound, ready to limit the spread.
Okay, let's switch gears from the factory spec to the site reality. That's governed by CSA A371, the standard for masonry construction.
Right. A165.1 dictates the block, but A371 dictates the installation.
And the first thing on site comes right back to the manufacturer's promise, dimensional tolerance.
It does. The block's width and height must be within plus or minus 2 millimeters. The length's within plus or minus 3.
2 millimeters sounds tiny, but for a mason laying a long course, that plus or minus 2 mil on the height is everything, isn't it?
It's the difference between laying to a clean line and fighting the course all day long. That consistency allows you to maintain a clean 10 millimeter mortar joint. If your block height is all over the map, your whole wall geometry is compromised.
Let's talk about joints that move versus joints that don't. This has big fire safety implications on site.
A huge one. We have to differentiate between dynamic joints and static joints.
Dynamic being
Movement or control joints. They're engineered gaps meant to accommodate movement from temperature, moisture, settlement.
And if that's in a fire-rated wall?
It requires a specific listed joint fire stop system.
What does that look like?
It's a special assembly. Often it's ceramic fiber felt or a similarly compressible fire-resistant sealant that can maintain its rating even after the joint moves. It's a specialized install.
And a static joint, like a T-junction or an L-corner, where things need to be rigid.
In those rigid connections, the walls are tied together, filled solid with mortar or grout. Because they're fixed, the National Building Code interprets this as cast in place.
So you don't need a separate fire stop system.
You do not. The tight, solid fit of the intersection itself effectively seals the opening against fire spread.
That is an excellent site efficiency detail to know. Saves time and money. Okay, last thing, reinforcement. When we need steel and grout, cell alignment is key, obviously. But what about the wire in the mortar joint?
Here's a fascinating technical conflict. The NBCC, for fire protection of steel columns, might recommend a wire with a cross-section equivalent to 5.21 millimeter diameter.
Okay.
But if you look at the construction standard, CSA A165.1, it limits joint reinforcement to a maximum of 5 millimeter diameter in a standard joint.
So wait, the performance code suggests a wire size that the installation code says you can't actually use.
In the standard joint, yes.
How do you solve that problem on the ground?
It requires an engineered solution. The designer can't just spec the 5.21 millimeter wire. They have to calculate and specify an alternative, often a smaller diameter wire spaced more frequently, to get the same total steel area.
So you're satisfying both standards.
Yeah. Exactly. It's a classic case of balancing design intent with construction feasibility.
What an incredible deep dive. We started with 4 cryptic symbols, H15AM, and we've broken them down into the fundamental blueprint for a CMU's performance.
The 4 facets: solid content, strength, density, and moisture. They really are the key.
They tell you if the wall will meet structural, thermal, and construction requirements.
And we learned that even subtle choices, like the aggregate type, have massive, sometimes counterintuitive results. Lighter blocks, for instance, often outperform normal weight blocks in a fire.
Which raises our final thought for you to chew on. The discussion clearly showed that lightweight concrete blocks can achieve a higher fire resistance rating than normal weight blocks of the same size.
So why wouldn't you always use them?
Exactly. Why might a designer still choose the heavier normal weight block for a residential tower or a commercial building?
And it really comes back to mass. The heavier the unit, the better the wall's acoustic performance. The need for a superior sound transmission class rating, an STC rating in a condo or an office.
It often outweighs that slight advantage in fire rating.
It's a trade-off, a classic engineering trade-off between fire safety and noise control.
Food for thought indeed. Remember, a wall is only as strong as its weakest facet. Know your codes, keep your plumb line tight, and we'll catch you on the next lift.